Hello, in this video we're going to look at maximum and minimum values. Okay, so let's start off with some definitions. So we're going to define a local max. Occurs at point A, B. If f of x, y is less than or equal to f of a, b for all x, y near a, b. All right, so visually, what does that say? So that says that if we, let's just draw ourselves a little picture. So if we have a point A, B, and then above it there's some surface, which we don't need to go through and draw. You can just go through and just pick a point here and say, let's say that's f of AB. Then what it's saying is if you take points that are near AB, right? So if we just pick that point there, so it's an xy that is near AB. And if you were to go through and plug it into the function, then the output is going to be smaller than f of AB, right? So if this distance here from here to here is f of AB, then the distance from here to here is going to be less than that, all right? So the output is smaller, right? And if you pick a point here, then that's going to produce an output that's smaller. If you pick a point here, then that's going to produce an output that's smaller, and so on. That if you pick points that are all around AB and plug them in, you're going to get smaller outputs. And so if you think about what shape that would form, is it would form a shape that looks kind of like this. You're going to get like a little peak, like a little mountain peak. It's a little difficult to draw there, but get the idea. I could draw it bigger over here and it would maybe make more sense. So you've got like that shape in the x direction, and you've got that shape in the y direction, and so you get a mini peak. Okay, so that's a local max. That's our definition for a local max, is that it occurs at AB if all the outputs for f of xy are smaller than the output for f of AB for all points xy near AB. Okay, so a local minimum occurs at AB if f of xy is greater than or equal to f of AB for all xy near AB. So it's effectively the same picture, just in reverse, right? So if we were to go through and give ourselves a little sketch, if we pick point AB, and we put up here, we put f of xy, or sorry, f of AB. And so this time we pick points that are near AB, that are around it, and you plug them in. And this time all the outputs are going to be greater than, like bigger than the output for f of AB. So you're going to get, you know, output up here and an output up here and an output up here. You're going to get all these outputs that are up above. And so in effect, what's going to end up happening is you're going to get a shape that looks, you know, kind of like that. All right, it's the opposite of this. So it's a little little valley as opposed to a little mini peak. Okay, so a local max looks like a little mini peak. Not pair, peak. And you get a little mini valley. When you have the local min. Okay, so those are our two definitions. Next, we have a theorem. If f has a local max or a local min, at a, b, and the first partials exist, then the partial with respect to x equals 0, and the partial with respect to y equals 0 at AB. That's at AB. Okay, so let's go through and prove this one. So what we're going to do to do the proof is we're going to go through and try and reduce the dimension of the 3D curve by setting one of the variables to a constant. And then once we've turned the 3D, or what I should say, the 3D surface, we're going to try and take the 3D surface and make it into a 2D curve by setting one of the variables to a constant. And then once we've turned it into a curve, we're then going to use Calc 1 theorems. So it's a common practice in multivariable calculus is to go through and use all of the results that we derived from Calc 1 as much as possible. And so that's what we're going to do. All right, so how do we do that? First, let's go through and write down the information we have. So we're going to suppose f of AB is a local max slash min, and the first partials exist. That's our given information, and then we need to go through and use that to end up showing that the partials equal 0. A partial with respect to x and the partial with respect to y equals 0. Okay, so step 1, we're going to let g of x equal f of x comma b. All right, so this is what I just said. If you didn't catch the audio, sometimes it's difficult without a visual to catch that. But what we're going to do is we're going to take the surface and we're going to turn it into a curve by setting y equal to b. So what effectively this does. So if you were to go through and kind of sketch the surface, we'll just sketch a hypothetical surface. But let's say we've got our surface. And we've got AB. If we go through and just kind of head up to the curve here, boop, 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 up to the curve, up to the surface, sorry. If you go through and say, I'm going to take my surface, which is f of x, y, and I'm going to just plug b into it for y, right? If you plug b in for y, then what you're doing is you're using our technique from quadric surfaces to create a cross section of the surface, right? So think back to quadric surfaces. When we covered quadric surfaces, you go through and to graph the surface, you set either x equal to a number or y equal to a number or z equal to a number to go through and create a cross section. So what we can do here by taking y and setting it equal to b is it's going to take this surface and it's just going to cut through it and create a cross section. And what that cross section is going to look like, so it's going to look something like this. Actually, let's do that in a different color. It's going to look something like this. All right. And that's now it's in 3 dimensions, but if you think about it, it's a curve now, right? If you were to go through and take the endpoints of that and just extend them down to the XY plane, right? So what you've got here is you've got a curve that's sitting on a plane. If you looked up the y-axis at this, right? If you looked at it this way, it would look exactly like a Calc 1 style curve, right? You wouldn't see any of this 3D stuff. You would just see this curve, and you'd have a z-axis and you'd have an x-axis, and that would be it. So so effectively what we've done is we've taken our surface and we've turned it into a curve. All right. And so this function g of x is this curve. Okay. And so that's the first step, is to go through and set y equal to b in the function, making the surface into a curve, then define that curve as g of x. Okay. So since okay, hold on. Whoops. I'm skipping a step. Well, actually, that was the right word to write, though. So since f of a b is a local max, right, then g of a must also be a local max. Why would that be? I mean, maybe I think that's kind of obvious, right? So if we go back, right, if f of a b looks like this or like this, okay, and you were to go through and you were to take the cross section of that, then you're still going to have either a peak or a valley. It's just going to be a 2-dimensional peak or a valley instead of a 3-dimensional peak or a valley, right? Does that make sense? So if we went through and we were to cut through this object, with by setting y equal to b like we did here, then what you'd get is you'd get this shape here for your cross section. So it'd still be 2 dimensions, right? If you looked at it up the y-axis, you'd still see just 2 dimensions, and you just would see a curve that looked like that. So you'd still get a peak, or in this case, it's going to be kind of messy looking, but if you were to extend this downward, this is what you'd see. So you'd see a little valley in our 2-dimensional surface if you looked up the y-axis. All right. So yeah. So if f of a b is a local max or a min, then g of a is still going to be a local max. It's just 3 dimensions, 2 dimensions. Okay. And then next we can go through and say, since g of a is a local max / min, we know that g prime of a equals 0. So this is a Calc 1 result. It comes from a Calc 1 theorem. So you could go back and look at that if you're interested. But it just says, so if we have, so we could go back one more time here. If we have a shape that looks like this or looks like this, okay, then the derivative has to be 0. So we have to have a flat top, right? So you have to have a flat bottom there. The slope of the tangent line here at the top is going to be 0. right? And so we rely upon that in Calc 1 quite a bit. Whenever you're looking for local maxes or local mins, you always look for places where the derivative equals 0. So that's something that I think is common knowledge. But if you're interested in that, you can go back and take a look at that Calc 1 theorem. Since if g of a is a local max or min, then g prime of a needs to be 0. Okay. Oh, actually, I should add one more thing here. Since g of a is a local max, g prime has to equal 0, assuming that the derivative exists. There is a way to have a local max or a min where the derivative does not exist. So I think that's actually part of the theorem, is that if you go back and look at the Calc 1 theorem, it says assuming that g of a as a local max or min and the derivative exists, and the derivative has to equal 0. So that's just a little extra detail there, but why not add it? Okay, so that does not complete the proof. All right, so what's the rest of the proof? So we have now that we're there, we can just go ahead and say, if we have g of x equal f of x comma b, and you differentiate both sides. So if you differentiate the left side, we're differentiating with respect to x. And if we differentiate the right side with respect to x, we have to use a partial derivative because there's it's a 2-variable function here. And so here on this, so we get g prime of x, right? And over here on the right side, we get the partial of f with respect to x, right? And then at that point, we can go through and plug in. So we want to know, we want to know what the result is here for a, for x equals a. So we could plug in a. And then we know from from what we just generated that g prime of a equals 0, so we get 0. And that's completes the proof, right? So, well, actually, I should say it completes half the proof. So it completes the part where we show that the partial with respect to x equals 0. We showed partial with respect to x equals 0. We did not end up showing the partial with respect to y, but it's effectively the same proof, just where you go through and you set g of x equal to a comma x, f of a comma x, and then everything else is pretty much the same. So, I mean, what does the proof say? It just says that you could take this Calc 1 result that works for 2 dimensions and you could extend it to 3 dimensions. That's all it says. So it's just a very complicated way of going through and saying that we can take a Calc 1 result and just extend it to 3 dimensions. Okay. Next, we are going to define what's called a critical point. The critical points are used in Calc 1 as well, so this should be a familiar definition. Or familiar idea, I guess I should say. Familiar idea is defined to be point AB such that the partial with respect to x at AB equals 0 and the partial with respect to y at AB equals 0. So it's any point where the partials equal 0. Let's go through and do an example of how you could find such a point. So let's say we're asked to find the critical points. So we have f of xy equals x squared minus 2x plus y squared minus 4y plus 10. So suppose we had a function and we're asked to go through and find the critical points. Then to find them, so critical points is the point AB where the partials equal 0. So you want to go through and just find the partials and set them equal to 0. So the partial with respect to x is going to be 2x minus 2. Partial with respect to y is going to be 2y minus 4. And then we can set each of these to 0. So if you set if you set 2x minus 2 equal to 0, and you set 2y minus 4 equal to 0, what happens? You get 2 equals 2x, and so we get 1 equals x, and you're going to get 4 equals 2y, and then 2 equals y, and so 0.12 is a critical point. Okay, so that's our definition of a critical point. It's really the same definition from Calc 1, just extended to 3 dimensions. So we've got 2 partials instead of a single derivative equal to 0. And the way that you find it is very similar to the definition from Calc 1. You just take the derivative, in this case 2 derivatives, and you go through and you set them equal to 0 and solve. All right, and so that's how we go through and get critical points. All right. So what do we know? So going back, we just said that, actually, hold on, it's here, theorem. If f has a local max slash min at AB and the first partials exist, then the partial derivatives are both equal to 0. And then we just said, if the partial derivatives are both equal to 0, then we call that a critical point. So tying those two together, if f has a local max slash min at AB and the first partials exist, then you have a critical point at AB. So we're just tying those two together. Okay, so the issue that comes up here, that sometimes logically, is people want to go through and they want to redirect the logic the opposite way. So you can't do that. So what is this? It's important to understand what this statement says. So if we have a local max slash min, then we have a critical point. It does not say if we have a critical point, then we have a local max slash min. All right. So what we need to do is discuss how do we go through and determine which critical points are local max slash min and which are not? Okay, so just redirecting that. Critical points are not all local max slash min, but some are. So you may be sitting there thinking, wait, what? So it's possible to have the partials equal 0 and not get a max or a min? Yes, it is. So let me show you that before we try and answer this question. All right, so yes, so you could go through and have the shapes that we drew initially. So you could have, a shape like this and a shape like this. So this is a max in the x direction and a max in the y direction. So we have a max in both x and y. And in that case, yes, if we had the partial with respect to x equals 0, the partial with respect to y equals 0. So yes, we do. This case does would be a case where we have a max. So you could go through and draw a little, partial with respect to x equals 0, partial with respect to y equals 0, and you get that shape. And yes, we could go through and have the opposite of this for a min. You could have a valley in the x direction. You could have a valley in the y direction. And in that case, yes, we would have our place where the derivatives, our partials equal 0, would produce a max or a min. But those aren't the only possibilities. You could have a max in the x direction, and you could have a min in the y direction. It's going to be a little hard to visualize this, but this is supposed to be the x direction. That's why I'm drawing it where the bottoms are kind of parallel to the x-axis. And then in the y direction, you could have a minimum. Okay, so you could have this case where it's a max in the x and a min in the y. So this is called a saddle point, and the reason is that you could draw a little guy sitting on a saddle, right? His legs are spread very far apart because of the way I drew the max in the x direction. He's spread eagled. He or she is spread eagled on the horse. But the idea is that you could sit on the point, and the horse would go this way, would be directly below the, this would be the saddle, part of the saddle that's sitting on the horse, and this is the part of the saddle that's holding you in place. So yeah, this is called a saddle point. And it is possible. You can have shapes that look like this, where you have a max in one direction and a min in the other. And this does, if you go through and were to check the partials here, you do have the partial with respect to x is equal to 0, and the partial with respect to y is equal to 0. So it does have the same kind of shape as the previous two in terms of that factor. And so that's a possibility. So that clearly is not a local max or a local min. It's a max in one direction and a min in the other. And you can have the opposite. All right, so you could have a max in the y direction, so that would look like this, and then you could have a min in the x direction, which would look like this. Again, I'm trying to represent the x direction by having the tops here be parallel to the x-axis. Okay, and so this is another type of saddle point. And so our guy this time is sitting this way. He's looking toward us. So this guy is, or she, this person's looking to the right. I guess it could be looking to the left too. This guy is looking toward us or away from us. Okay, and so in this case you have a max in the y direction, and you have a min in the x direction. Okay, and so you can see, based upon these wonderful pictures, I'm an artist, you could see that it is possible to have partials that equal 0 in the x and y direction, and yet not have a maximum or a minimum. Okay, yes, critical points can be maxes and mins. Critical points can be saddle points, though, as well, instead of being a max or a min. Okay, so how do we determine which critical points are local maxes and mins and which are not? Enter the second derivative test. Not to be confused with the second derivative test from Calc 1. The second derivative test says, suppose point AB is a critical point. So you've gone through and you found your critical points, And you're trying to figure out which critical points are max and mins and which are saddle points. All right, so suppose AB is a critical point and the second partial derivatives exist. Oh, hold on, sorry, second partials are continuous. All right, here we go. So what we're going to do, so the second derivative test is a little complicated. You're going to define point D, maybe point D, value D, function D. You're going to define D to equal second partial at AB times second partial at AB minus the mixed partial at AB squared. All right, and then A, if D is greater than 0, and the second partial with respect to X is greater than 0, then f of AB is a local min. B, if D is greater than 0, and the second partial, oh, whoops, what am I doing? It's not a good idea to ignore your notes and just start ad-libbing when you're creating a video because it's very distracting. Is a local max. And then C, if D is less than 0, then f of AB is a saddle point. And then D, if capital D equals 0, then the test is inconclusive. Okay, so there's the second derivative test. It's a little bit complicated. So you've got to go through and create this thing, this construct, D, and then based upon the output of that construct, we can then go through and combine it with information about the second derivative to say whether we have a local max or a local min. So that's really interesting. Why does that work? Right? Why does the second derivative test work? I will do my best to explain why I think that it works. It's going to take about probably 10 or 15 minutes. So you might want to fast forward through this part if you don't really care about these explanations. But it's interesting. It's interesting why it works, or at least why I think it works. All right, so we're going to have to go back to Calc 1 and recall some stuff. Right, so you learned some stuff about how the derivatives affect the shape of the graph of the curve, right? So we're talking about Calc 1. Let's see, what can we say about that? We know that f prime of x is the slope of the tangent line, right? right? But we could also go through and say that it describes the rate at which f changes. Right, as you go from left to right on the graph. Right, so for example, if we were to say if f prime is greater than 0, then we know that the curve has a positive slope, or that f increases as you go from left to right. So if f prime is greater than 0, then we know f has a positive slope, or that f increases. This is important. The second part is important because we're going to use the second part more than the first part. Or f increases as you go from left to right. As the curve, the function, whatever you want to call it, goes from left to right. Right. This is a long way of saying that it has, we know that the shape goes upward as we go from left to right. Okay. So we can go through and say, and just take that. So we're going to take the second part more than the first part, more than the positive slope. We're going to take the second part and we're going to use that. So if we were to go through and say the second derivative, right? So the second derivative equals the derivative of the first derivative, right? And so what the second derivative describes is the rate at which f prime changes from left to right. All right, so that makes sense. So it's the rate at which f prime changes. In other words, if we were to go through and say if the second derivative is greater than 0, then f prime increases as the curve goes from left to right. And what is f prime? Well, f prime is the slope of the tangent line. So what the second derivative, if the second derivative is positive, it tells us that the slopes are increasing. And so if you were to go through and draw that, you would draw something like you draw, a flat slope and then a increased, a steeper slope and then a steeper slope and then a steeper slope. So the slopes increase as the curve goes from left to right if the second derivative is positive. And that's how you get that the fact that the second derivative gives the concavity. All right, so is because that's our definition for concavity is this shape, right? So it's like if you have a bowl shape for the curve, then that's our definition for concavity. Okay, so these are both things that we do need. Maybe you already knew all that stuff, but we're going to go through here quickly and apply this to multivariable calculus now. All right, so let's do that. So we can go through and say the partial with respect to x is the slope in the x direction or it's the rate of change of f in the x direction. And in this case, we mean the positive x direction. So, and so just to be crystal clear here, if the partial with respect to x is greater than 0, then the slope in the x direction is positive. It's a little hard to go through and sketch a picture that would represent that, but if you had, so this is the x direction, right? And then the slope would have to be positive, so it'd have to be rising as you went in the x direction. So as you moved this way in the x direction, the positive x direction, the curve, the z coordinate of the curve is increasing, so you're rising. So this is a z, small z distance, and then a larger z distance. Okay, or you could interpret this the second way: the rate of change of f, f increases as we move in the x direction. Okay, so the partial can be interpreted either as the slope or as a rate of change. If it's the slope, then the slope is positive. If it's a rate of change, then the rate of change is just saying that the underlying thing increases as we move in the positive x direction. So the rate of change definition is change in z over change in x. And so if change in z over change in x is positive, then the change in z increases, all right, is positive for a positive change in x. Okay, so hopefully that made sense. Anyway, so let's move on to what's the second derivative. So if we have the second derivative with respect to x equals the derivative of x differentiated with respect to x. So what is that? All right, that's going to be the rate of change of the partial with respect to x in the x direction. So it's describing how the partial with respect to x, the inside thing, the underlying thing, how that changes as you go in the x direction. So that's the thing that ties in here, right? So what does the partial with respect to x say? It says that you take this thing, if you want to rewrite this is using the similar. So it's, you have this underlying thing, and you go through and you calculate the derivative in the x direction, and what it does is it says how that underlying thing changes as you go in the x direction. And so we can do the exact same thing here, but just with the underlying thing be the partial with respect to x instead of the underlying thing be the function itself. So the derivative, the second derivative, is going to be the rate of change of the partial of f with respect to x in the x direction. So what does that mean? If the second derivative is greater than 0, then the partial with respect to x increases as we move in the x direction. All right, so let's draw a little bit more formal picture because it's getting a little bit complicated, right? So let's say we have a picture like that. And we've got some starting point here. Let's use a different color to make it a little bit easier to see. All right, and then so what I'm going to do is I'm going to use arrows for my slopes. So you could think of it like we're using vectors now for the derivatives. And so let's say we calculate the derivative, the second derivative here, and it's greater than 0. That means that the underlying thing, the first derivative, which is the slope in the x direction, it is increasing as we move in the x direction. So let's say here we have a little mini, that's our first slope in the x direction, and it looks like it's 0. And then our second slope in the x direction needs to be greater than that. And then our third slope in the x direction needs to be greater than that. And so what you end up with is you end up with a shape that looks like that. And so what the second derivative with respect to x finds is it finds the concavity in the x direction. So it's this same picture here, except it's just the slopes here are now all in the x direction. They're in the x direction. Okay. And so this still, so the second derivative with respect to x still gives us a measure of concavity. All right, and if you're thinking, oh, that's really complicated, why not just say that? That you could just extend the Calc 1 result. That's because we're not done. All right, so where things get really confusing and interesting, I think, is if you go through and you find the mixed partial. All right, so what is this geometrically? All right, well, let's go back. What was this? So this was the rate of change of the partial with respect to x in the x direction. So that means this is going to be the rate of change of the partial with respect to x in the y direction. Okay, so this thing here is going to be, it tells us what the direction is, right? So here, if we go back to our to the first definition, we said this is the slope in the x direction, right? This little sub x, that says the direction. So we're going to get the slope in the x direction, or it's the rate of change of f in the x direction, right? X direction goes with this. The second derivative, it's the rate of change of the partial with respect to x in the x direction. So this gives us the direction, and then this is the underlying thing. Direction, underlying thing. Underlying thing is f. Direction is the partial. So if we go through and just apply that, underlying thing is the partial with respect to x, and we're finding the way that it changes as we go in the y direction. Hopefully that makes sense. So where this gets confusing is if we go through and have this and we say, well, if it's greater than 0, then what does that mean? Right? So what we want to do is just do, again, just apply the same thing. So then, so when we did when we did two derivatives with respect to x, you had the f changing, the partial with respect to x increasing as we move in that positive x direction. So here we're going to have partial with respect to x is increasing as we move in the y direction. All right, so what on earth would that look like? All right, so this is the whole point of all of this, is to figure out the mixed partial. Well, so let's see if I'll try and draw a picture here, see how this goes. This worked really well on paper, but I don't know if it will work very well in the program. Okay, so is the rate of change of the partial with respect to x in the y direction? Well, what is the partial with respect to x? What's the slope in the x direction? So this is saying the slope in how the slope in the x direction changes as you go in the y direction. Let me write that down. Slope in x direction, that's the partial with respect to x, and how it changes as we go in the y direction. All right, so let's see if we can go through and handle this. All right, so let's suppose we have a 0 slope here at the origin. So I'm going to draw a little red arrow like that. That's a 0 slope. So usually I'm trying to hovering a little bit above the point just to make it easy to see. Okay. And now what we're going to do is we're going to move in the y direction. So we're going to move over here in the y direction a little bit. And now what this is saying is that if the mixed partial here is greater than 0, then that partial with respect to x should increase. The partial with respect to x is the slope in the x direction. So the slope in the x direction should increase. And so what we should see is we should see a positive slope. So a positive slope is a little bit goofy looking, but it should look something about like that, right? So it should be upward pointing a little bit. And if you make it a little bit easier to see the upward pointing, if I were to go through and maybe put like a dashed line down here. So imagine this is flat, this is the x direction, and this is the amount of vertical height for the arrow. So it's pointing upward. And if you keep going in the x direction, then that slope continues to increase. And so if we go a little further, we should get a steeper slope. And again, I'll try and draw. So this is the x direction. And then, so this shows how that it's steeper. So this is the vertical change here. This is the z direction change. And then, so you can see the z direction change is even larger, right? And if you went in so this is in the positive direction, the slopes get bigger. If you go in the negative direction, then they should get smaller. So let's go through, let's actually draw a negative x-axis or negative y-axis. All right. And so if you go over here and you draw, so we should get a negative slope. So if this is flat, then we want to have something about like that. So that's pointing downward. That one maybe is the hardest one to use your imagination on. So if you could imagine, this is the x direction. And then this is the amount of negative z direction that's going, that this is pointing downward. So this is flat, this is up, this is down. And so let's see if we could do one more here. And so if you keep going, you should get even larger. Whoops. Yeah, this is way easier to do on a piece of paper. You should get an even steeper negative slope. And so if you go over, you can see that the amount that this is pointing downward, so this is flat, this is x being flat, this is the amount of downward z direction for that vector, right? And so you get this shape. So this is what happens if the mixed partial, the derivative with respect to x, which is then differentiated with respect to y, is greater than 0, then that's saying that the partial with respect to x increases as we move in the y direction. Thus, if we were to represent the slope with vectors, this is where the partial with respect to x would be 0. The slope in the x direction is 0. Slope in the x direction is as we move in the y direction, becomes a little bit positive, more positive. So the slope in the x direction is increasing as we're moving in the y direction. And the same thing is true here. It's just, if you think about starting here as you go, this is a large negative, less negative, 0, positive, positive. So the slope is increasing as we move in the x direction. Okay. So that's what the mixed partial does. What does that tell us about the shape of the graph? It's a little hard to tell. So let's go through and do the same thing with y. I'm kind of giggling because I think this is fun. All right, so if you go through and say this is greater than 0, then what this is saying is that the partial with respect to y is increasing as we move in the positive y direction, or in the positive x direction. So what is the partial with respect to y? Well, that's the slope in the y direction. So we have the slope in the y direction is increasing as we move in the x direction. All right, so let's see if we could go through and represent that with slopes too. And we're going to put it on the same picture. Let's use blue. Why not? All right. So here, slope in the x direction. I guess it's going to kind of covering. I'm going to slide it over a little bit so it's not sitting on top of this curve next to it. The slope in the y direction is 0 here at the origin. All right. So you move in the positive x direction, you get a steeper slope. All right. So we should get should be pointing upward. Let's exaggerate it a little bit more. All right. And so if you want to put some dashed line on there. So you can see there's the y direction. That's flat in the y direction, and it's got a slightly upward slope. All right. Let's go through and and then if you keep going in the y direction, you get a even steeper slope. Let's see, is there a way I can make that look steeper? It doesn't look very steep. Now it's kind of sitting on top of the x-axis. Anyway, you get the idea. So let's go through, and the dashed line there would be like this. So there's the y direction, and that's the amount of vertical change in z for the vector pointing in the y direction. And if you went in the negative x direction, then you'd get downward pointing arrows. So this is slightly downward and then more downward, like that. And so you could go through and maybe say, all right, so hold on. That's supposed to be with black. So you could see the amount that's pointing downward, and then you can see this one's pointing downward even more. All right. Now, just a comment. So you notice I said, oh, well, the mixed partial is greater than 0 for x. And so that says this. And then I just jumped immediately and said, okay, well, I can also assume that the mixed partial the other way is also greater than 0. Well, don't forget the theorem from a couple sections ago that says that the mixed partials are equal. All right, so if you have one greater than 0, then you inherit the other being greater than 0. Okay, so putting all that together, the question is, what does this shape describe? Look at this. What is this shape? What does it look like is happening here? Okay, so if you were to try and draw a surface onto this, so that's what we did with the previous examples, right? So I drew some curves. I drew some arrows, and then I drew a curve to try and fit onto those arrows. You know, I drew some slopes, and then I drew a curve to try and fit on it. So what type of curve would fit onto all of these arrows? Think about it. So the way that I go through and look at this is that if you think about what's happening, so it's easy to see what's happening on the axis, right? So you can see that you have on the axis, as you go in this direction, the slopes are increasing in the y direction. Now, it doesn't say anything about what's happening in the x direction, but it says that's what's happening in the y direction is you're getting this type of shape. So it's a little bit hard to interpret what that means on the x direction. But what we can interpret is if you think about between the two, right? So let's use yet another color. How about pink? The question is, what's happening between the two? What's happening above this line here? I think that's easier to actually interpret. And then we're also going to look at what's happening above this line here as well. What's happening on those lines? Well, if you're going this way, you know, toward this pink line, you're going upward, right? You're climbing up a surface. That's what this arrow represents. It represents the fact that the slope in the x direction is positive at that point on the y-axis. So you'd be climbing this way, right? What if you went this way? You'd be climbing, right? So if you're climbing here and you're climbing here and you're climbing less here and less here, and you know, we're just saying, for instance, that the point here at the origin is on the curve, then what it's saying is it's saying that the curve has to curve upward as we go. So this black line is directly above the pink. It has to go upward, right? Because you have to rise as you go in this direction, right? That's what this blue arrow says. It says as you go this way, you've got to rise to the surface. As you go this way, you've got to rise to the surface. And so you get this type of a shape. And now think about what's happening on the backside here, right? So if you went this way, you're dropping, you're declining, right? See how the blue arrow is pointing downward? So you're falling as you go this way. And if you go this way, you're declining, you're falling as you go this way. So if you're declining, right? If we go this direction, that means that you must have been up above the surface so that you could walk downward as you went this way. And so you end up getting the corresponding shape on the backside. So we get a curve that looks like this if it's going to fit, this general description, that you'd rise as you went this way and rise as you went this way and decline, like walk downward as you went this way and this way. So if you're declining as you walk downward these two directions, then you had to be above the surface in order to walk downward. Okay. And now, so what about, so that handles this quadrant and this quadrant. What about over here? Well, let's think about what's happening as you're going that direction. So as we go into this quadrant from this side, you're going downward. And if you just reversed these arrows, what's happened is if you're going upward as you go from left to right, then you must be going downward as you go from right to left. So if this is pointing downward and this is pointing downward, right? If you went the opposite direction of this, then the curve must have been below the pink line. And then the same thing over on this side. If you were to go through and think about going this way, if when you go from top to bottom, you're going up, if you go from bottom to top, then you must be going down. It's the opposite. So this way, we're going down. This way, you reverse these and you're going down. So thus, the curve must have been below the pink line. And so what do you see there? You've got above the first and third quadrant, if you were to think about looking downward on this, you've got a upward curve, and in the second and fourth, we've got downward. And so the mixed partials, if you go through and look at what the mixed partials represent, they represent a saddle point type structure. The more positive the mixed partial is, the more this accentuated this structure is going to be. All right, and so now if we go all the way back to, maybe that was more than 15 minutes, maybe that was half, I don't know, it was a long time. If we go all the way back, why does the second derivative test work? Okay, so let's take a look, and I'm just going to write on here. So this piece, what we just said, this is a measure of saddle point. What is this? This is concavity in x direction. What is this? This is concavity in y direction. So put it all together. What you have here, the first part, this is saying if the concavities agree, if they're both positive, then you'll get a positive number out of this. If they're both negative, then you'll get a positive number out of this. So just ignore this piece for now. If you've got concavities that are both positive or both negative, then D will be positive. All right. And if D is positive, then you've got a local max or a local min, right? If they're both, if the concavity is positive for X and positive for Y, right? What does that tell you? Positive concavity is this shape. So we've got a local min, right? So positive concavity in the X, positive concavity in the Y. Positive times a positive is a positive. So we're going to get a positive D. What does it say for a positive concavity? Local min. All right. What if they're both negative? If the concavity in the X direction is negative and the concavity in the Y direction is negative, then the product of a negative times a negative is going to be a positive. So we're going to have a positive D. And what does negative concavity look like? Negative concavity in the X, negative concavity in the Y. And so we get a local max. So what this first piece does is it's going through and testing, do the concavities agree? Are they both positive or are they both negative? If they're both positive or both negative, then we have a local max or a local min. If they're opposites, if one is positive and then the other one's negative, well, what does that look like? Positive concavity in the Y, negative concavity in the X, saddle. Negative concavity in the Y, positive concavity in the X, saddle. So when the concavities do not agree, you get saddle points. Concavities do not agree. Positive times a negative is a negative, so you'll get a negative D. Thus, you get a saddle point. All right, so if the concavities do not agree, then that's when you get the saddle point. That's when you get the negative D. Now, the thing that adds complexity to this is this second term, which we've been ignoring. So what did we just say? That's a measure of saddle pointness, but it's a saddle pointness kind of on the diagonal. Like instead of on the x-axis and y-axis, it's a saddle point off of the between the two, on the line y equals x and y equals negative x. And so what this says is that you could have the concavities agree, and you could have something that looks like this, right? But it turns out that the saddle point structure off of the X or Y is so strong that it overwhelms the concavity in the X or in the Y. And so what it's saying is that if we went back to this picture here, it could look like this, but we could still, because of the shape off of the X and Y, it could still be a saddle point. So if you were to go through and draw the pink line that we drew on our picture, if you were to go through and draw those pink lines, so here and here, then let's see if I can manage this. So below this one, you could have, so below the pink line here, this the pink line for the second and fourth quadrant, you have it agrees with the picture of the concavity in the X along the X-axis and the Y-axis, but then between the two, we have this shape over here. And so it turns out that you could still have a saddle point, but the saddle point is off of the X-axis and the Y-axis. So that's a very, very long and detailed explanation for why the second derivative test works. That's my explanation. I've never seen that explanation in any textbook, so I don't know, maybe it's wrong, but that's the way that I understand it. And I think it provides a lot of conceptual depth if you understand all of that. So I think it's really interesting and good stuff to look at. All right. Moment you've all been waiting for. What about doing homework problems? All right, so let's do some examples. So suppose you've got a function. All right, and you're asked to go through and find local max, local min, and saddle points. So first we go through, and to do that, what you have to first find before you can use the second derivative test, what do we need to have? We need to have critical points. So you need to first go through and find the critical points. So partial with respect to x, derivative of xy with respect to x is going to be y minus 2 minus 2x. Partial with respect to y, derivative of xy with respect to y is going to be x minus 2 minus 2y. Set these equal to 0. 0 equals y minus 2 minus 2x. 0 equals x minus 2 minus 2y. In order to solve this, what you can do is go ahead and solve one of these and then substitute into the other. So you could get, move these two to the other side, and we'll get y equals 2x plus 2. Pop that into this other guy, and you'll get 0 equals x minus 2 times 2x plus 2. And we get 0 equals x minus 2 minus 4x minus 4. And then we'll get, what is this? This is a negative 3x minus 6. So we get 6 equals negative 3x. Then x equals negative 2. Then take that x and plug it in over here, and we'll get y equals negative 4 plus 2, or y equals negative 2. So we have x equals negative 2 and y equals negative 2. So our critical point we have negative 2, negative 2. Once you've got the critical points, you need to go through and construct that formula for D, that really complicated looking formula. So we need to create this thing here. So you need the second derivative with respect to x, the second derivative with respect to y, and the mixed partials. Second derivative with respect to x. If we differentiate this with respect to x, we get negative 2. Second derivative with respect to y, differentiate this with respect to y, we get negative 2. Mixed, differentiate this with respect to y, we get 1. Put it all together, d of x comma y equals negative 2 times negative 2 minus 1 squared. And so the formula is equal to 4 minus 1 is 3. Now there's no x's or y's here. That's not going to happen every time. You could have x's and y's here. That's totally allowed. So sometimes you do need, most of the time you do need to plug your point in. It's just this is a really easy example to start with. All right, so anyway, so we could say d of negative 2 comma negative 2 equals 3, which is greater than 0. Right? And so what does that tell us? It tells us that our concavities agree. We're going to have a max or a min. Well, our concavities would agree, and the mixed partial, the saddle point behavior off of the x and y axis was not strong enough to offset it, right? So we did get a little bit of that action going on, though. And so we have, okay, sorry, d is equal to 3, which is greater than 0. So that tells us our concavities agree. We're going to have a max or a min. And then the question is, which do we have? Well, we look to the second partial with respect to x for that. That's equal to negative 2. And since that is less than 0, right, if you go back to the previous, earlier in the video, I'll do it right now. I'll do it right now for you. All right, if d is greater than 0 and the second partial with respect to x is greater than 0, min, d is greater than 0, second partial with respect to x is less than 0, max. So which one did we have? Less than 0, so this is the local max. All right, and so that's how it goes. All right, so the way these problems work, you first need to find the critical points, take the derivatives, set them equal to 0, solve, get the point. Then to use the second derivative test, we need second derivatives, find them, put them together into this formula for D, plug in the point. If it's greater than 0, then that tells you you're going to have a max or a min. And the way to tell which one is the right answer is to look at the second partial with respect to x. A good question is, does it have to be the second partial with respect to x? Could you look at the second partial with respect to y? Yes, you could. There's nothing special about the second partial with respect to x. It's just you need to use one of the two. It doesn't matter which one you use. Let's do another example. We get x cubed plus y cubed minus 3x squared minus 3y squared minus 9x. Find the local max, min, and saddle points. All right, so to do that, we need to go through and find the partial with respect to x. So that's going to be 3x squared minus 6x minus 9. Find the partial with respect to y. 3y squared minus 6y. Set those equal to 0. This time the variables are entirely separate, and so you can just solve the two equations separately. So this is and over here we've got, all right, and then we could go through and factor x squared minus 2x minus 3. That's x minus 3, x plus 1. And we could factor. And then so the solution here, we're going to get x equals 3 or x equals negative 1. And here we're going to get y equals 0 or y equals 2. So what are our critical points? Well, so x could be 3, and you'll get the partial with respect to x will be 0. Y could be 0 or y could be 2, and you'll get the partial with respect to y to be 0. So we need to have 3, 0, and 3, 2. And same thing for negative 1, right? So negative 1, 0, and negative 1, 2. So you get 4 possible points. All right, next we need to go through and find the second partials. Okay, so we get 6x minus 6. Second partial with respect to y, 6y minus 6. And then we get the mixed partial, 0. All right, we can construct the equation for D. This times this minus this squared. And then we could plug in points. So if we plug in D of 3 comma 0, right? So what are we going to get for that? We're going to get 18 minus 6. That's going to be 12 times negative 6. So we get negative 72. So negative 72, we don't even need to go any further. So that's going to be a saddle point. So we're going to have a saddle at 3 comma 0. And then D at 3 comma 2. So we're going to have 12 times 6. That's going to be positive 72. So that's greater than 0. And then we're going to need to then check what's our second partial with respect to x. We said that that was greater than 0. Oh, hold on, let's do it this way. So that equaled 12, which was greater than 0. So thus we have local min at 3, 2. And then D negative 1, 0. So if we plug in -1, right, we're going to have -12 and then -6. So we're going to get +72, which is greater than 0. Second partial with respect to x, what did we say it was? -12, which is less than 0. So we get a local max at -1, 0. And finally, -1, 2. So -1, 2, we're going to have -12 and +6. So -72, less than 0. So we get a saddle. All right. And then I went through and I did one more. All right, same instructions. We want to find local max, min, and saddle points. All right, so go through, find the partial with respect to x. To do that, we're going to need to use product rule. So we get the first times the derivative of the second plus second times the derivative of the first. And we're differentiating with respect to x here, so we're going to get 2x. And then we're going to need to simplify that. So that's going to become -x squared plus 2x minus y squared times e to the -x. Partial with respect to y. No need for product rule, so x are treated as constant, so this e to the -x, the whole thing just is treated as a constant. And then we just differentiate the x squared plus y squared with respect to y, and we get 2y. So we get 2y e to the -x. All right, so set those both equal to 0. So we're going to get 0 equals -x squared plus 2x minus y squared e to the -x. And let's do it them next to each other. 0 equals 2y e to the -x. All right, so first of all, these exponential terms can never equal 0, so you can just get rid of them. The way that you justify that, you multiply by e to the x on both sides, and those will go away. Or divide by e to the -x on both sides. And so we're left with this. So we have 0 equals -x squared plus 2x minus y squared. And 0 equals 2y. So 0 equals 2y, we could solve that. We get 0 equals y. Once we have 0 is forced to equal y, you could take that and plug it into the other equation. And what happens if y equals 0, we get -x squared plus 2x. And so you can go through and solve that. We're going to get 0 equals -x times x minus 2. So we get x equals 0 or x equals 2. Okay, so that's the critical points. We get 0, 0, and 2, 0. All right, and then we need to go through and find the second derivatives. So we have second derivative with respect to x. And so to do that, you can go through and take our first derivative with respect to x and differentiate that with respect to x. You need to use the product rule again. So we're going to have -x squared plus 2x minus y squared times -e to the -x. I don't know why I drew that little parenthesis. And then first time, so that's the first times the derivative of the second plus second times the derivative of the first. And we're differentiating with respect to x here. So we're going to have -2x plus 2. All right, and we're going to need to simplify that again. And so if we simplify that, we're going to want to take this and combine it with this. Let's see, what are we going to get here? So we've got negative x squared. That's going to be a positive x squared. And then we're going to have a negative 2x, right? And then another negative 2x. So we're going to have minus 4x. And then we're going to have a double negative here for y squared. So we're going to be plus y squared. And then we also have this plus 2. And the second partial with respect to y. So differentiate this with respect to y. So 2e to the negative x is all constant. And then the derivative of y is just 1. And then the mixed partial. So you could take this first result and differentiate it with respect to y, or you could take the second result and differentiate with respect to x, because they're equal. So that's what I'm going to do. I'm going to do the second one. And so if you differentiate that with respect to x, the y is treated as a constant, so you get 2y, and then the derivative of e to the negative x is negative e to the negative x. So we get negative 2y e to the negative x. All right, and so now we can take all of that and can create our formula for d. So d of xy is going to equal x squared minus 4x plus y squared plus 2 e to the negative x times negative 2y e to the negative x. Oops, hold on. That's the wrong one. Wrong one. Times 2y e to the negative x. Sorry, I did it again. Times 2e to the negative x times this guy right here, the second partial with respect to y. And then minus this guy squared. And let's see, can we just, is it easy to just plug in? All right, so if you plug in 0, 0, what's going to happen here? This is all going to turn into 2. E to the 0, 1, so just ignore that. This all turns into 2. All right, and then minus, and then this all turns into 0, right, because of the y. So we get 4. And what was the sign of that? So the second partial with respect to x, what was that? It was 2, right? So it equals 2. So 2 is greater than 0. So we get a local min at 0, 0. Okay, and then rather than go to another page, let's just do the second part over here. All right, so we're going to have d of 2 comma 0. Right, that was our second critical point. What happens with that? All right, so we're going to have 2 squared minus, well, let's just write it out. So we're going to have 4 minus 8 plus 0 plus 2 times e to the negative 2 times 2 times e to the negative 2. And then since y is 0, the second part still drops out. We get minus 0 squared. All right, and so what is that? So that's 4 minus 8 is negative 4 plus 2. We got negative 2. Negative 2 times positive 2. So we're going to have negative 4 e to the negative 2 times e to the negative 2. Not that that matters, but that's going to be e to the negative 4. And so that's less than 0. So because of that, we have a saddle point at 2 comma 0. Okay, so that concludes the video. Thank you for watching. See you next time.